Okay, so today we are moving on to inference with means. So everything that we've done previously has surrounded proportions and categorical data. We did our one sample z test, our one sample z intervals, we did the two samples, chi-squared even had to deal with categorical data. Now we are moving on to means because most of the time you are dealing with proportions, but there are occurrences where quantitative data is the only kind of data we can collect. And we do have inference methods for those types of data. It is all following similar patterns to what we did with um, z intervals and z tests. But we do have a different kind of distribution. A lot of the characteristics of t distributions are going to follow both a combination of z-scores and chi-squared values kind of jumbled together. So today we are going to talk about the one sample t interval. First thing we have to go over is what is the t distribution? Well, a t distribution is going to look very, very similar to our z distribution. Remember, a z distribution is unimodal, it's symmetric, it has one peak, tapers off at the ends. Well, our t distribution is symmetric, it's unimodal. The big difference here is that it has more area in the tails. So it's not going to taper off and be very, very small probabilities in the tails all of the time. So one thing where it kind of falls in line with chi-squared and what we just did in Unit 8 is there is a different t distribution for every sample size. And we get this t distribution by using degrees of freedom, similar to what we did with chi-squared. We used the degrees of freedom to kind of determine how about like what was the probability of our test. So we do something exactly the same with t distributions because every single sample size is going to create a different t distribution. So I have a little image over here that kind of talks about how they look like visually. We're always going to be centered around 0. That's going to be a characteristic that carries over from z distributions. And as I have smaller sample sizes, notice how round and how much area I have in the tail of my distribution. As I get closer to 30, my distribution gets pulled up and it starts to look a little skinnier. I'm losing some of that area in the tails. And as we get higher and higher in sample size, our distribution is going to eventually look very similar to the Z distribution. And that's kind of what we want because with the normal curve, with the unimodal symmetric model, we are able to easily calculate probabilities given that we're centered at this standardized value, at this 0, and then going out standard deviations. And as the degrees of freedom increase, the t distribution approaches the standard normal density curve. So basically, we are going to hopefully have sample sizes large enough that allow us to kind of take on the properties that we've used for normal curves, where we can calculate probabilities given some critical value. And the test statistic T is much like the test statistic Z. It's going to function exactly like a Z score. Now, you will hear me call it a T statistic. You'll sometimes hear me call it a T score. It's the same thing. It's just the cutoff value for our probability. And as it represents how far x bar, which is our sample mean, is from the mu, population mean. So what we do with our confidence interval, it's going to follow panic. It's going to be the same process where we are defining parameters, checking assumptions and conditions, naming the test, calculating the interval, and concluding. However, you have to be careful because we've been so ingrained with doing things with proportions, we use proportion symbols. It is very, very important that when you are doing means, we're using x bar and we're using mu. If you happen to throw a p or a p hat in there for the AP exam, they will mark it wrong entirely because it has to follow means. So x bar, mu, very, very important, and t. Don't call it a z score; it is a t because we're working with the t distribution. So let's go ahead and go over the construction of a confidence interval. You are very familiar with this. it is the exact same thing we do for proportions, just some slight differences. So, one thing I do want to remind you of is we calculate confidence intervals to give an interval of plausible values for an unknown population parameter. We're trying to figure out, based on this one sample, can I estimate what the true mean in this case is going to be for the entire population? That one sample is going to create an interval that gives you a range of what it could be. Now, it's not telling you that it has to absolutely fall in there. That's where the confidence comes in. Higher the confidence, the wider the interval. Smaller the confidence, smaller the interval. So now we are building confidence intervals for quantitative data, numbers, not categories, using sample mean, X bar, as our point estimate, which we'll get into once we start looking at the formula. Now, defining parameters, it's going to function the same way. Big key difference, we're doing mu. We're not doing p. I know you want to do p because we've been doing p for the last 2 months, 2 or 3 months. We're switching to mu, changing gears. Now, assumptions and conditions. The nice thing about this is we've kind of worked with sample means already. We did it when we were working on sampling distributions in Unit 5. So we have gone through this process of checking conditions before. It's just reminding you what we have to do. The nice thing with most of these tests that we go through in stats is there are two conditions that you can pretty much count on every single time. Randomization, was our sample selected randomly, or were our treatments applied randomly? We have 10% condition. Can we assume that the population is greater than 10 times the sample size? 10% condition can sometimes be replaced with, if you feel like it doesn't fit, we do have that possibility to say we can kind of assume that each sample, each person that we have surveyed, or each person we're collecting data from, is independent of each other. And that typically happens when we're doing experiments. We can say one result isn't going to necessarily affect another. Therefore, they're independents. Because randomization and 10% together are trying to satisfy that independence assumption. And then we have our nearly normal condition. So basically, the goal of most of these tests is to try to mimic a normal model. And there are three ways that we can do this with means. The nice way, the most favored way, I would say, is they tell you. If they say it's normal, we agree that it's normal. We're not going to go in and double check and verify. If they, in some part of the problem, say this distribution is represented by a normal graph, great, awesome, move on. Now, second best option is we can say that the central limit theorem applies, which basically tells us that if n is large enough, and that large enough number is if it's greater than 30, we can assume that the distribution is going to take an approximately normal shape. And that comes from this idea that as my n gets bigger, it's going to start looking more and more normal. Then, third option, probably the least favorable, is if they give you data, generally they want you to graph it and double check that it is a normal distribution. Typically, we do this with a histogram or a box plot, which we will kind of go through and do a refresher on today. But basically, you're looking, does it have any strong skew, and are there any outliers? So that's the goal for visual representation. Ideally, they tell you. Second best, central limit theorem works. Third, not favorable, is you have to graph it. And with this visual representation, you will have to graph and include a sketch. So in your formal answer on the AP exam, you should sketch out your box plot or your histogram. Typically, I'm going to advise box plot just because it's easier to label and sketch, but you have to write it on your paper. You just can't say, yeah, it's normal, and move on. They have to visually see that you verified it. And if you get a sample size less than 30, we only use T procedures if there are no outliers and no strong skew. So we will have to make sure and double check and verify that all of those values are meeting those two conditions. Or yeah. But typically, with mean questions on the AP exam, they will make sure that either they've stated it or that central limit theorem works because they don't like you entering in data into your calculator, processing a lot of numbers. It kind of allows for too much variation in correct answers. Well, too much variation in answers because lots of calculator error can happen. So we've gone through P and A. N, naming the test. Again, this is a one difference between what we've done before and what we're doing now. This is a one sample T interval. And now we move on to calculating the interval. So remember, we take a point estimate, we add and subtract the margin of error. The point estimate is a statistic, meaning it comes from the sample. Since we're dealing with samples, our X bar is our sample mean. Generally, if they want you to do a confidence interval problem, they are giving this to you in the problem unless they have provided you with data that you have to go in and find yourself. Plus or minus margin of error. Margin of error is critical value times the standard error of a statistic. So standard error, and why it's not standard deviation, basically is just because it is built around a statistic value, not a population value. So we have our T star, and T star is going to function just like our Z star. However, remember, this is particular to each sample size. So we will not have that nice shortcut where we knew if I'm calculating a 95% confidence interval, it's always going to be 1.96. We don't get that luxury with T distributions. We have to calculate T star every single time. And we use the sample standard deviation over the square root of n. So that's going to be our standard error. Okay, now how do you quickly find the T star value? So what we will do is we will use something similar to inverse norm. If you go to your calculator and you do second vars number 4, which is going to tell you inverse T, it's going to ask you two things. It's going to ask you what's your desired area and how many degrees of freedom do you have? Well, desired area we're familiar with. I included 3 popular ones, 90%, 95, and 99%. Remember, the interval is always going to be the center. We have two cutoff values, a negative T star, a positive T star. These two values are the same. One's just negative, one's positive. So it does not matter which one you find. Typically, I always find the positive one just because that's what I like to do. Does not matter which one you find because you are doing plus or minus, so you get both options either way. So for 90%, my desired area to get the positive T star value would be 5% plus 90.95. 95% interval would be 0.975, and a 99% interval would be 0.995. Now, that's going to be kind of a common thing, is just depending on your desired interval if the question asks, you can enter the same areas. Where it gets different is actually going in and entering in the degrees of freedom, and that's just our sample size minus 1. So just a quick sketch, and I will upload these notes at the end of the day if you don't want to struggle with trying to figure out a way to put it into your digital notes. These will go up eventually. But this is kind of where our inverse T is coming from. I will show you how to manually fill in the formula, but we'll also talk about how you can get your calculator to do the formula for you. Stating our conclusion in context, same idea. We can be, however, percent confident that the interval from lower bound to upper bound captures the true mean. Don't forget population parameter in context. Don't write proportion. We're dealing with means. Gonna try to break you of all of the habits we've kind of built already. Now, one thing that often comes up in or on the AP exam is how can I determine sample size given a specific margin of error? So before we move on and actually go through a test, I am going to kind of go over one of these problems. I will say more often than anything, you will get a sample size problem with a proportion interval, not means, because means are very, very special. So here is my formula for margin of error. It's the t star n minus 1 times sample standard deviation over square root of n. Well, the issue with margin of error and going in and filling in what I know to solve for n, which is what we do when we have proportions, is I run into the problem of, in order to get a correct t star value, excuse me, I have to know what the sample size is to begin with. So in order to get this value, I need to know what n is. Well, I can't do that because I'm trying to figure out what the sample size is to begin with. So we do a little bit of variation on the formula, and we do it using the normal model procedures. So I'm going to take a population standard deviation, and I'm going to, basically what I did is I went backwards and I solved for n. If I were to replace, let's see, if I were to replace my t star with a z star, and if I were to replace a sample standard deviation with a population standard deviation. So basically went backwards, divided by my z star, square rooted, all of that good stuff. Or yes, squared, I mean, sorry. Now, one thing to remember when we are dealing with sample sizes is we always want to round up. Cannot round down, because then you won't necessarily meet the margin of error you're interested in. Always round up. And I'm only going to do one with you guys because typically, again, a question like this is going to come from proportions and not means on the AP exam. So, health teachers at Richardson High School want to estimate the body mass index of female students at RHS. The BMI of young American women follows a normal distribution with a standard deviation of 8.1%. How large of a sample is needed to estimate the mean BMI of RHS female students within 3% with 98% confidence? Well, from this question, they've given me a population standard deviation of 8.1. They've given me a margin of error of 3%, and they've told me they want to be 98% confident. So, symbol wise, population standard deviation, I'm going to change these to decimals just because generally when you're presented with percents, that's what they want you to do because it's easier to kind of calculate and work with. Margin of error 0.03, and I want, or they want, to be 98% confident. So basically my interval needs to span 98% of the possible plausible values. And I have two cutoff values, a negative z star, a positive z star. And if you remember, when we're doing a problem like this, we are using inverse norm. So if I have 98 in the middle, I have 1% in this tail. So I always do the positive one. Inverse norm of the area of 0.99, mean of 0, standard deviation of 1. Not going to change anything there. And this is going to be approximately 2.3263. So what I do now is I take what I know. Population standard deviation, margin of error, z star, and I'm going to plug it into my formula for sample size. Now, the unfortunate thing about this formula is it's not on your formula chart. However, they do give you the pieces of the margin of error. You just have to work backwards and solve. So I'm going to plug in my values, and then I take this, put it into my calculator. Be very careful because you are doing a fraction within a fraction. I always use that alpha y equals function just to make sure my work is organized, and this gave me approximately 39.4511. And with sample sizes, we always round up. So that's at least 40 RHS female students needed to be within 3% of the true value. So your margin of error is equivalent to 3%. Again, I would be surprised if this is the approach that they take. I would be more inclined to believe that they ask a question like this with proportions, where you don't have to necessarily rely on using a different distribution critical value or changing the different measure of standard deviation. But it's nice to see, remind you of the process. Now we are going to actually go in and calculate and construct a confidence interval. So, going to move on to example 2. Okay, the Tribal Urban District Assessment is a government-sponsored study of student achievement in large urban school districts. TUDA gives a reading test scored from 0 to 500. A score of 243 is a basic reading level, and a score of 281 is proficient. Scores for a random sample of 1,470 eighth graders in Atlanta had a mean score of 240 and a standard deviation of 42.17. They want us to construct and interpret a 99% confidence interval for the mean reading test score of all Atlanta eighth graders. So we are going to kind of go through these steps of panic. First thing we want to do is define our parameter. Parameters describe the population. For mean, that symbol is a mu. Mu is equal to the true mean reading test score of all Atlanta eighth graders. That's what we are trying to estimate with our confidence interval. We're going to go through and check our conditions. And the two first ones, random sample and 10% condition, are satisfied. Random sample of 1,470 eighth graders. And we can assume that there are at least 14,700 Atlanta eighth graders. Atlanta's a big city. I'm going to assume that that's fair. With our third condition, our nearly normal condition, I was not told that it's normal, so I moved to my second option of checking the central limit theorem, and my n is equivalent to 1,470, which is greater than or equal to 30. Therefore, central limit theorem applies, approximately normal. If you can kind of remember in the back of your brain when we did sampling distribution of means, it was very, very important that you stated central limit theorem applies. You can't just say n is bigger than 30 and move on. You have to say in writing on your paper, CLT applies, it's approximately normal. If you just tell them the sample size is greater than 30, they're going to say, yeah, it is, but what does that mean? You have to kind of expand on it. I just know that that's something that's commonly missed on tests and things like that. Make sure you're writing the actual statement. Okay. Method, one sample t interval. I went ahead and included the formula that we will be using. You have the option of doing this by hand or in the calculator. Of course, first I'm going to show you how to do it by hand, and then we'll talk about calculator steps in just a second. So, first thing I'm noticing, I know X bar. X bar is 240. That's my sample mean. I know S. That's 42.7. Sample standard deviation. I know N. The one missing piece to this formula is the T star value. So I need to find T star of 1,469 because that's my degrees of freedom. So what I'm going to do is I'm going to kind of walk you through this one in the calculator. So because I'm doing a 99% confidence interval, remember, let me draw a picture really quick. 99 is in the middle. Oops. And then that means I have 0.5 in the tail. No, 0.05. 005, sorry. There we go. Math. If this is 0.99. So in order to get this T star value, I need to enter in an area of 0.995. So let's go to the calculator. I'm going to walk you through this one time. Second, bars, and then number 4, inverse T. So I'm going to enter in my area of 0.995, and my degrees of freedom is 1 minus my sample size minus 1, so 1469. And I'm going to paste and hit enter. And it's telling me that the corresponding T-star value is 2.5792. So that's what I'm going to record on my paper. And I'm going to plug in what I know. I know my X-bar, I know my T-star, my standard deviation, and my sample size. Don't forget to square root the sample size in your denominator. Plug all this into my calculator. That's going to give me a lower bound of 237.1632 and an upper bound of 242.8368. The calculation for that is just plugging it into the main screen, making sure everything is in the correct place. Always be careful with your fractions, and calculating the lower and upper bound. Once I have my confidence interval, I'm going to go ahead and interpret. We can be 99% confident that the interval from 237.1632 to 242.8368 captures the true mean reading test score of all Atlanta 8th graders. Same process, same procedure. The big changes are the actual formula we're using, what we're plugging into our calculator, and just symbols for the most part in comparison to our one proportion interval. Now, with the calculator steps, I did write them out, and you can take a note on them. The most important thing that you know is that we're using stat tests number 8. With means in particular, you have the option of being given data or being given statistics. So dependent on whether they give you a table or whether they tell you the mean is this, the standard deviation is this, you have two options. With data, you're just going to enter your data into L1. I did make a note, leave frequency at 1, don't change it, should stay at 1 all of the time. They do ask you the degree of freedom, but again, it's just n minus 1. For stats, you're going to have to enter in the sample mean, the sample standard deviation, and the sample size in order to have the calculator run the test for you. So what I'm going to do is I'm going to try to split screen this really fast. So I'm going to show you and verify that our answer is correct. Let's see, there we go. So I'm going to go to stat. I'm going to go over to tests, and then I'm going to go down to number 8, to T interval. And we don't have data, we only have stats. So I'm going to go over to that side. The X bar for this problem was 240. The standard deviation was 42.17. And the sample size was 1,470. And then we wanted a 99% confidence interval. So I'm going to change that. And I'm going to hit calculate. So that gave me 237.16. Yep, basically the same. 242.84. Basically the same. Yes, there will be a little bit of rounding error, mostly because we did round off this T-star value. Again, they do have a range of acceptable values on the AP exam that they take. And I can guarantee you this type of difference is not major to them. Now, if you're getting something like 235, that's something where they're going to have to double check and verify all of your steps. Which they do. They do go back and follow your work. All of the AP stats exam is graded through, meaning they follow along with your process. So, with confidence intervals, often we are asked, What can you decide? Based on your interval, what conclusion do you make? So, based on the interval, is there convincing evidence, which signals typically for us a hypothesis test, that the mean reading test score for all Atlanta eighth graders is less than the basic reading level? Justify your answer. One thing I do want to say here, if on the AP exam they indicate based on your interval, and instead you go through and you do a hypothesis test and you get a conclusion, more likely than not, they are not going to give you credit. It has to answer based on what they want, based on your interpretation of your confidence interval. They're not asking you to do a hypothesis test. They're saying use the interval you just calculated to answer this question. So, my interval is from 237 to 242. The basic reading score is 243. My entire confidence interval, my entire range of plausible values is less than the basic reading level. So the entire confidence interval is below that score of 243. Therefore, there is convincing evidence that the mean reading test score for all Atlanta eighth graders is less than the basic reading level based on our confidence interval. So this isn't one sorry, this isn't one where we have two proportions. Remember, we were very keen on whether or not our interval contains zero. That's a difference problem. With the one sample T intervals, it's how does it kind of relate to what they want? Is it all below? Is it all above? Does it capture the value that they're claiming? That's kind of what you're paying attention to when you're seeing, does your interval support your conclusion or your idea or your claim? Gonna give you a little bit of time to write, about 20 more seconds. Okay, let's move on to our last example. Miss Contreras' car records the fuel efficiency in miles per gallon and resets every time she fills up her gas tank. She randomly selected 20 samples of fuel efficiency from her car's computer. Construct and interpret a 95% confidence interval for the mean fuel efficiency for Miss Contreras' car. So, I am trying to find the true mean fuel efficiency for my car. Now, some things I'm noticing immediately, I have a table of data. Generally, that's a signal that I'm going to have to graph something. I also only have a sample of 20, so I do need to verify that there's no strong skew and no outliers in my data. So I'm going to go ahead and start off my confidence interval. The mu is the true mean fuel efficiency for Miss C's car. I do have a random sample, it's stated, and I can assume that there are at least 200 samples in my car's computer. I've filled up my car way more than 200 times, I'm pretty sure, can almost guarantee. Now, the third condition, the nearly normal condition, is going to have to be checked using graphing. We're going to have to go into our calculator and graph the data. So I'm going to open mine up. Now, I have already gone in stat edit, and I've entered in the 20 data values. So you can kind of follow along. If you want to type yours in, just kind of make note of the steps so that you can verify you're doing it correctly. And I want to look at either a histogram or a box plot, either one. So I'm going to go to second, y equals, and notice that my plot 1 is off. Can't have that happening, so I'm going to go enter, and I'm going to turn plot 1 on. And here is where you have your options of what you would like to do. I'm going to go ahead and just do a box plot. Oops. I think they're the easiest to sketch. It's going to ask, where are your values? It's an L1. What's the frequency? We leave it at 1. Once you've selected box plot, all you have to do is hit zoom 9, and you're going to get your box plot. So one more time, second, y equals, make sure plot 1 is on, select box plot, and I always select the one that is calculating outliers, the one with the 2 little dots next to it. Leave your X list as L1, zoom 9. Now, I just need to sketch this. This looks to be a pretty normal, no strong skew, no outliers box plot. So I just need to sketch this on my paper. What I do is I hit trace and I record the 5-number summary. So the minimum is 242, 25.6, 26.5, 26.9, and 28.4. And I sketch on my paper something that looks very similar to that distribution in my calculator. So I do try to follow the same shape, and I just label the 5-number summary. I state that there is no strong skew and no outliers. Therefore, we can assume this is approximately normal. Yes, if in some off chance they require you to graph and verify on the AP exam, you have to sketch a picture. Do I think that that's something that they would do? Most likely not, because of the fact that you could very easily type in 258 instead of 25.8, and everything's wrong. Everything's thrown off. So, most likely you will not have to do this, but I do like to remind you of how to graph box plots in your calculator. We are doing a 1 sample t interval. So I'm going to go back to my calculator really quickly. And I've already got my data in the calculator, so I'm going to do stat tests. I'm going to go down to number 8. And this time I don't have stats, I have data. So I'm going to select data. It's asking me, where's my list? I'm telling it it's an L1. What's my frequency? It's 1. What's my confidence level? This time I want to be 95% confident. So I'm going to change that. And then I'm going to hit calculate. Now, when I say that you need to be recording your computer's output, this is the window I'm talking about. You do not have to write your computer's input, but you do need to include everything that comes out of that screen. Write down the sample mean, write down the sample standard deviation, write down n. Just reiterate what your calculator is telling you, because graders can kind of figure out, well, their mean's a little bit off. Most likely they entered in a value wrong, not just they're completely wrong entirely. So you want to give them that support to potentially allow you to have some more credit if your interval happens to be wrong. We can be 95% confident that the interval from 25.742 to 26.738 captures the true mean fuel efficiency for Miss C's car. Yes, calculator is perfectly fine. If you are a person who likes the formulas and the algebraic process of the formulas, that's awesome too. Either method gets you the same amount of credit. Just remember what everything means when you're having to type things into your calculator. You don't want to type in the wrong thing and get an incorrect interval.